condenser is there. Uh, 054, give me the host ship.
Yes, sir. 1 second, sir. Done, sir.
Okay, who is your CR?
064 Animesh.
Animation 06 06
4.
Okay, so I've made him the host, no problem.
You have made 060 co-host.
Sorry, 1 minute. 064. Where is 064?
So I had unmuted myself.
One my co-host.
Yes, sir, done.
Okay. Okay, no issues. Let me switch on hotspot if in case. So Animesh, please allow the students after confirmation in the class. Okay.
Yes, sir.
Okay, thank you. So in the last lecture, we learned about the few basic concepts of this basic thermodynamic. We talked about what exactly mean the thermodynamic. Then we also try to understand the law of conservation of energy, that is also called as first law of thermodynamic. Then we talked about the second law of thermodynamic. Then there are different approaches of the to study the thermodynamic. It is called a classical thermodynamic and the statistical thermodynamic. Then we learn about different application areas of the thermodynamic. Then we talked about the different types of the systems, or what exactly mean the system surrounding boundary and universe that we generally used to consider inside the thermodynamic. What is exactly the concept of that? Then we talked about the fixed and movable boundaries. At the same time, we also talked about the imaginary and the real boundaries. The systems are classified into three different categories. Closed system, that is called as control mass system. Then what you can say, the control volume system, that is called as open system, and isolated system. So in the closed system, energy transfer from system to surroundings is possible. Okay, so energy can cross the boundary of the system, but mass is not allowed to cross the boundary of the system. Okay, so in such type of case, if cases are there, then that type of system we generally call as closed system. In open system, both the energy and the mass, both the parameters are allowed to cross the boundaries of the particular system. And in isolated, both are not. We also talk about different examples associated with the closed system, that is called pressure cooker, then water heater, then we can say the thermos flask. All these are the what categorized under closed system, open system, and isolated system. Okay. Then I think we covered properties of system. Yes or no? Yes.
Yes, sir.
We also talked about the different properties of the system, that is called as intensive properties and the extensive properties. The properties which are independent of the mass of a system, we generally call as the intensive properties, and which are dependent on the mass of the system or size or extent of the system. All such type of properties we call as the extensive properties. Specific properties are the extensive properties per unit of mass. Then we talked about the density and the specific gravity. Then I think up to this we finish. Is it? Yes or no?
Yes.
Okay. Now we not talked about the equilibrium, no? Okay, hold on.
Yes, sir, we don't.
Not done.
Not done, no? Okay. So not system, the state and equilibrium. So in the thermodynamics, there is a one concept called as state and the equilibrium. So thermodynamics basically deals with equilibrium state. So we'll try to understand what exactly means the equilibrium state. But before that, we must need to understand the equilibrium. What exactly means the equilibrium? A state of balance. It is called as a particular equilibrium. So here in this particular the case, the equilibrium in the thermodynamic is basically related to unbalanced potential. That unbalanced potential may be with respect to thermal aspect, maybe with respect to the mechanical aspect, maybe with respect to the phase, or maybe with respect to the what we can say chemical aspect. So if in the thermodynamic, if you are saying that the system is in the thermodynamic, then there should not be any unbalanced potential associated with the thermal, mechanical, phase, and chemical. What exactly mean the thermal equilibrium? If the temperature is the same throughout the entire system. Okay. If the temperature is not same throughout the system, that means unbalanced potential obviously are there in the system, and we can't say that the system is in the thermal equilibrium. Suppose take the example of this particular container. Okay. So everywhere the temperature is different, 20 degrees Celsius, 23 degrees Celsius, 30, 35, 40, 42. But after some time, the temperature is balanced, okay, and we are able to maintain a temperature called as 32 degrees Celsius. When you switch on the air conditioner of any room, at different point, the temperature is to be different. But after some time, okay, after 1 hour, 2 hour, or 3 hour, the particular temperature is to be, the average temperature is to be constant, okay, and is to be same in that particular room. So that is we generally call as a thermal equilibrium. Second is nothing but called as mechanical equilibrium. What is mechanical equilibrium? If there is a no change in pressure at any point of the system, okay, with respect to time. So irrespective of the time constant, if there is not any change in the pressure of a system, then that is we generally call as a mechanical equilibrium. So pressure, force, okay, or pressure we generally used to consider, okay, as unbalanced potential in the mechanical equilibrium. Third is nothing but called as phase equilibrium. So if a system involves two phases, and when the mass of each phase reaches an equilibrium level and stays there, then that type of equilibrium we generally call as the phase equilibrium. So in this particular case, in the phase equilibrium, take the example of water get converted into the water vapor, okay, or in the steam. So for a long period of time, okay, the phase associated with the water which get converted into steam is the water, that is liquid phase, and the vapor, that is called as a steam. And both the phases used to be in that position, in that state for a long period of time, and it is the equilibrium. So that type of equilibrium is generally called as phase equilibrium. Last one is nothing but called as chemical equilibrium. What is chemical equilibrium? Chemical equilibrium, if the chemical composition of a system does not change with time, that is no chemical reaction occur. So if that happen, then obviously that type of equilibrium is generally called as chemical equilibrium. So what is the example of an iron rod, and that iron rod is in the, suppose take in the container, okay, where the water is there in the water bath, and that water bath is open to atmosphere. Then after some period of a time, okay, obviously oxidation will start and erosion, corrosion will come to picture. That means chemical reaction happen. That means the particular system is not in the chemical equilibrium. So if you are in the thermodynamic, if you are saying that the system is in equilibrium, that means we are assuming that, or we what we want, or we are expecting that there should not be any unbalanced potential of associated with the thermal or mechanical or phase, and what we can say chemical. Getting all of you? Yes or no? Any doubt in this? Any doubt?
No, sir.
Okay. Then a state postulate. What is state postulate? The number of properties required to fix the state of a system is generally called as state postulate. Okay. The state of a simple compressible system is completely specified by two independent intensive properties. Okay. So nitrogen, that is nothing but the state of nitrogen is fixed by two independent intensive properties. Okay, that is called temperature and specific volume. So what we can say here, any two properties independent, any two properties we required in order to define that particular state, and that is nothing but called a state postulate. What exactly mean the simple compressible system? A simple compressible system is if a system involves no electrical, no magnetic, no gravitational, no motion, and no surface tension effect. If that system is satisfy all this, then that type of system is called a simple compressible system. Now moving toward the few more basic fundamental associated with the thermodynamics, that is we generally call as processes and the cycle. So when you're going to talk about processes, what exactly in the process? The different processes are there. Okay. But before that, we need to understand what exactly in the process. The process, any change that a system undergoes from one equilibrium state to the another. So here we are in one equilibrium state, and here we are at the second equilibrium state. Okay, so when the system changes or undergoes from one equilibrium state to another equilibrium state, that is from 1 to 2, okay, then process happen in between state point 1 and state point 2. Provided when you are fixing a state point 1, that means the state point 1 is defined by the two independent properties, that is called, at that just now we talked about the state postulate, that is called as property A and the property B. So with the property A and property B, we are able to define the state that is in the equilibrium, okay, at point 1, and after a few time period or after the process or which happened, we are able to get the state point 2. At state point 2, the property A is different than the previous case. So we also having the new property at point 2, and new property B at point 2. So the process which happened in between state point 1 and the state point 1, then state point 2, then that process we generally call as a process. Okay, that thing we generally call as a particular process. Now, the series of states through which a system passes during a process. Okay, so here, if you go on to talk about the series of process may be in this particular direction, or maybe in this particular direction, or maybe in this direction, or maybe in this direction, or maybe in this direction. So we achieve the state point 2 through this path, or we can say through this path, or through this path, or this path. So this is nothing but called as a process path. To describe a process completely, one should specify the initial and final states as well as the path it follows and the interaction with the surrounding. So obviously, with the state point 1 and state point 2, we are able to define the initial condition and final condition. But how you achieve the state point 2, that is very, very important. Okay, and that we only come to know by defining the process path which happened between state point 1 and state point 2. Next is nothing but called as quasi-static or quasi-equilibrium process. When a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all time. Okay, so at all time, what we want? We want the process must achieve the equilibrium state. And what exactly the equilibrium state? Equilibrium with respect to thermal aspect, that is called the thermal equilibrium, then mechanical equilibrium, the phase equilibrium, and the chemical equilibrium. So in order to achieve the equilibrium from one state point to other state point, okay, then we require a lot of time or infinite time period we require. Okay, and obviously if infinite time period is involved, then process needs to move very slow from one state point to the other state point. And such type of process if happened, and if you are able to achieve the equilibrium at each and every state, then that type of process we categorize as quasi-static or quasi-equilibrium process. Suppose the example, the piston and cylinder arrangement. So this is the piston and cylinder arrangement. The piston is here. We have some working medium inside, or gas or air inside the cylinder, and then we have the cylinder. If the process happens very slow, then we are able to achieve the equilibrium at each and every state. But if the process happens very fast, then obviously we will not able to achieve the equilibrium, okay, at each and every state. And that type of process we categorize as the non-quasi equilibrium state. Okay, so if the process is categorized as a quasi-static, that means that process consumes the infinite period of time in order to move from state point 1 to state point 1. And series of that process if happen, then that is called as quasi-equilibrium process or quasi-static process. These processes are classified under different categories. Okay, so suppose the example on this PV diagram. This is the PV diagram, P versus V, and process takes place from initial point state point 1 to state point 2. So piston is here in the cylinder arrangement, piston and cylinder arrangement, piston is here, okay, which signifies the volume V1. And when you compress it, when the piston moves and when the piston is compressing the working fluid, okay, the compression will take place. And when the compression takes place, the volume will change from V1 to V2. But what about the pressure? Pressure will increase from P1 to P2. So process takes place between state point 1 and state point 2, okay, and we are able to get such type of process. So in this process, pressure is different. In this process, the volume is different, the temperatures are different. So the different thermodynamic properties behaves in a different way when process happen from point number 1 to point number 2. So by keeping one thermodynamic property as a constant and understanding the behavior changes on the with respect to other thermodynamic parameter, if that things happen, then such type of the processes we generally prefix which are called as ISO. ISO means keeping that term as constant and trying to observe the behavior of change of other thermodynamic properties on that thermodynamic plane. Okay, so some common properties are used, that is called a temperature, pressure, and the volume. The prefix ISO is often used to designate process for which a particular property remains constant. So if I'm saying that the process is isothermal, that means we are maintaining the temperature constant. If I'm saying that the process is isobaric, then I am keeping the pressure constant. If it's isochloric or isometric, then I am keeping the volume constant. If I'm saying the process is isentropic, okay, then I'm keeping the entropy constant, is also called as adiabatic process. And if nothing is constant, all things are get variable vary, then that type of process we call as polytropic process. And if this number of process, if you join together in such a way that the initial state is equal, if initial state if you are able to get the as equal to the final state, then such type of the process, such type of the thermodynamic thing we generally called as a cycle. So process during which the initial and the final states are identical, then that is called as a cycle. Any doubt in this?
No, sir.
Now moving forward, in the thermodynamics we have the different laws of thermodynamics. That is the first law of thermodynamics, second law of thermodynamics, third law of thermodynamics, and zeroth law of thermodynamics. The first law of thermodynamics tells us about the law of conservation of energy. Okay, second law it tells us about the entropy. Third law, temperature never be equal to zero. And the zeroth law of thermodynamics, why name is zeroth law? Because all the laws came into picture first, okay, and after that the zeroth law came into. Okay, so because of that, for all these laws, we require the foundation of the zeroth for we require the foundation of this law, and because of that, it is not possible for us to name it as a fourth law. Okay, they label this law as zeroth law of the thermodynamics. No other logic is there in order to put the zeroth name. Okay, that is zeroth law of thermodynamics. Okay, so the zeroth law of thermodynamics, what it tells us, if two bodies are in thermal equilibrium, body A is in the thermal equilibrium with the body B. If the two bodies are in thermal equilibrium with the third body, and both the bodies are in the thermal equilibrium with the third body, then they are also in thermal equilibrium with each other. Okay, so suppose we have a body A and body B, okay, and both are in the thermal equilibrium, and if you insert a thermometer inside that, then obviously the thermometer will also show the same temperature. Okay, that means the three bodies, they are in the thermal equilibrium with respect to each other. We have a body called as iron at 150 degrees Celsius. We have the copper at 20 degrees Celsius. The temperature will get maintained constant after some period of a time. Iron temperature 60 degree, copper 60 degree. So two bodies are in thermal equilibrium. And if you want to measure the temperature of this combined body of iron and copper, and if you insert it, and if you insert the thermometer, the thermometer will also show the same reading of 60 degrees. That means the two bodies are in thermal equilibrium with the third body, then all these three body, okay, they used to be in thermal equilibrium with respect to the each other. By replacing the third body with the thermometer, the zeroth law can be stated that two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in the contact. Now here they are in the contact, but even if they are not in the contact, then also, and if they show the temperature same, then all these three bodies used to be in the thermal equilibrium. So this is nothing but called as the zeroth law of thermodynamics. Now, other than this, there are different forms of energy. Okay, any doubt up to this?
No, sir.
All of you with me? Am I audible, clear, loud and clear?
Yes, sir.
Now, other than this, we need to understand the different forms of energy. Okay.
Sir, go with this slowly, sir.
Okay.
Yes, sir.
We need to understand different forms of energy. Different forms of energy means basically with respect to thermodynamics, these energies are we generally classified as work and heat, not potential energy, not kinetic energy, not we can say mechanical work or thermal work or electric work, not like that. The work and the heat, or heat and work. What is work? Work is one of the basic mode of energy transfer. Okay. In mechanics, we know that if you have the body and the force is going to act on the body, then obviously body will move in the direction of the applied force and work will take place. Okay, in simple mechanics. In thermodynamics, the work transfer is considered. Okay, that work transfer is considered as occurring between the system and the surrounding. Whatever the envelope you consider for the study and whatever things are there outside that envelope, that is called a surrounding. If there is an interaction, if there is a transfer of energy, okay, from system to surrounding or from surrounding to system, then that type of work we generally call as thermodynamic work. Okay, work is said to be done by a system if the sole effect on the things external to the system can be reduced to the rising of orbit. What is this? This is Joule's experiment. We'll discuss this Joule's experiment in detail. I think in the 11th and 12th standard itself, you talked about the Joule's experiment. Okay, we'll talk about that in detail in coming part itself. The work is done by a system, it is taken to be positive, and when the work is done on a system, it is taken on the negative. So if you're going to talk about the engine, we fire the fuel in the engine, we convert the chemical energy of the fuel into the heat energy. So that heat energy do the work on the piston will reciprocate. When piston reciprocate, shaft will turn. That means the work is produced in the system, okay, or work is produced by the system. So such type of work we consider as a positive work because it is produced, it gets converted into work. But reverse is true in the case of the motor. If you want to lift the water from low head to the high head, if you want to lift the water from low head to the high head, then is it possible to lift the water from low head to the high head only with the help of pump? No, that is not possible. Pump is always coupled with the motor. We require to start the motor. So electric energy get converted into the mechanical energy, and mechanical energy get converted into your fluid energy. Okay. So the external work is supplied to the system. अगर आप मोटर को निकाल देंगे तो it is not possible for a pump to transfer or to deliver the water from low head to your high head. Getting? Yes or no? All of you with me?
Yes.
Yes, sir.
Yes, sir.
Now, what is power? Power, the rate of energy transfer is known as power, or the rate of work transfer is known as the power. The unit of power is joule per second. Now, one more thing about the work. It is not at all possible for us to define the work at one state point. When state point 1 changes to state point 2, then and then we are able to say that work is done or work is absorbed in the system. Okay, so work is produced by the system or work is done on the system. We can say in this way. But what is the work at state point 1? Not possible. It is not possible for us to define the work at state point 1. What is the work at state point 2? No, unless and until process not happened between point number 1 and point number 2 on thermodynamic plane. Okay, it is not at all possible for us to define the work. It is not only work, it is a work done for a process between point 1 and point 2. It is not at all possible for us to define work at point 1 or work at point 2. It's a transfer, it's a work transfer from state point 1 to the state point 2. Getting all of you? All of you with me, yes or no, please?
Yes, sir.
Yes, sir.
Then energy. The energy, what we generally call as heat. Heat is the energy or energy flow. It is basically because of the temperature gradient, what we can say, or temperature difference. The flow of this energy takes place, or we can say heat is the energy flow resulting from a temperature gradient or temperature difference. Note that temperature and heat are not the same thing. What is the difference between heat and temperature? Yes. What is the difference?
So temperature is the measure of heat, I think.
The measurable parameter of content of heat in a system. Okay, we denote it with the temperature. Very good. Okay. So temperature is not, it's a measure of the parameter. Okay, it's a measure of heat we generally call as. But heat is an energy content in that particular system. Suppose an example, we have one beaker. In that we have some water. One beaker here where we have the ice. Here temperature is 100 degrees Celsius. We started to heat this water, okay, with the help of the fire, with the help of heat source. Water start to boil from 0 degree towards the 100 degree, and at 100 degree it starts to boil and start to get convert. And what about this? Here the temperature is 0 degree. Okay. So what will happen in between? If you have the copper rod, then the heat will transfer from this copper rod. Okay. The molecules inside the particular this copper rod will vibrate about their mean position, and they will transfer the heat from one location to other location, and heat will carried out from point 1 to point 2, point 3, and here itself. And here this particular ice, okay, start to melt and will try to get converted into the water. Okay, so by doing the experiment, we come to know that there is a heat flow. Okay, what is the direction of that heat flow? High temperature gradient, high temperature potential towards the low temperature potential from 100 degrees Celsius towards the 0 degree Celsius. Getting all of you with me, yes or no? Getting.
Yes, sir.
Now, reversibility. Okay. Reversibility is the ability to run a process back and forth infinitely without any losses. Very, very difficult to achieve such type of the process. We require very controlled environment or controlled volume, okay, in order to achieve this particular process. What are the different types of reversible process? Perfect pendulum, okay, without friction is the example of this reversible process. Irreversible process, dropping a ball of clay, okay. It is not possible for us to reverse the process and get the perfect ball again. It is irreversible, the process. Movie making, putting in the reverse and the forward without any loss of the track, okay, it is called as reversibility. So movies of reversible phenomena appear the same when played forward and the backward. Okay, this is not actual thermodynamic example, but we can correlate that example with our thermodynamic concept. Irreversibility is opposite is true. What are the various examples of reversible processes? First, perfect pendulum. Second, mass on spring. Third, dropping a perfectly elastic ball, it will jump. And perpetual motion machine. Perpetual motion machine is basically the machine which violates the first law of the thermodynamic and second law of the thermodynamic. The machine which basically able to produce continuous amount of the work without consuming any amount of the energy. Is it possible? Your machine is producing continuous work and you are not consuming any amount of the energy.
No, sir.
It is not at all.
No, sir.
Not possible. So that machine we generally call as perpetual motion. The machine which violates first law of thermodynamics and second law of thermodynamics is called the PMM of first kind and PMM of second kind. And many more are obviously there. Irreversible processes. What are the different types of the irreversible process? The dropping a ball of clay, hammering a nail, okay, applying the brakes to your car, breaking of a glass, and many more. Okay, you look here and there, you'll find the process is irreversible. In order to achieve the reversibility in that process, you require to create the control environment, and then it is possible to have such type of the reversible process. Otherwise, the process obviously will be the what we can say irreversible process. Popping of a balloon, not reversible unless energy is expended. So we require putting the air, blowing the air in the balloon. After some time, it will burst. So if you want to have the balloon again, we require some external agency, okay, some external force, some external energy we require to put into the system so that we must get the balloon again. But some external energy is required. What are the various sources of irreversibility? First, friction. Is it? Friction is the most important source. Second, what we can say? A voltage drop. Okay. Resistance, the pressure drop, temperature drop, concentration drop. Okay. So these are nothing but called as the various sources of various sources. All these sources, they're playing the major role in order to have the irreversibilities inside the process. Friction, then voltage drop, the pressure drop, the temperature drop, and the concentration particular drop. Okay, any doubt in this? Yes.
No, sir.
Okay. So in this way, we try to finish the basic fundamental concepts which are associated with the unit number 1. So unit number 1 basically related to all such type of the particular concept. Other than this, there are the certain few fundamentals are also required that we need to address. Okay, and these fundamentals, okay, we need to take in the particular, not in the PPT, but on the board. So I will take a board. Let me take a board. Give me 1 minute. This blank document is visible to all of you? Yes or no?
Yes, sir.
Okay. Okay, so now we'll move into the basic fundamental aspects with respect to CP, CV, and a perfect gas. Because if you not understand the perfect gas, it will be very difficult for you to understand the different type of the process. Because in the processes we generally used the fundamental of the perfect gas and the concept of CP and the particular CV. Okay, so here the CPCV or the first law of the basically the thermodynamic comes from the Joule's experiment. Okay, so we'll talk about the Joule's experiment also in detail, and we will have the derivation of the Joule's experiment where it says that the internal energy is the function of the temperature change. So that will also try to explain. Then we try to have a look on the relation called as Cp minus of Cv is equal to R and Cp by Cv is equal to gamma, and then we'll move on the different types of the particular processes such as isobaric process, isochoric process, then isothermal process, then adiabatic process, and then what we can say a polytropic process. Okay, so first is nothing but called as a perfect gas. So whatever things are going on the board, I advise all of you to please take down all these notes, okay, in your notebook, because I'll only share the PPT, but not all these notes. So I request all of you to please take down these notes also. Is it okay to all of you?
Yes, sir.
So first is nothing but called as a perfect gas. What is perfect gas? We know the characteristics gas equation of state. What is the characteristics equation of state? PV is equal to
NRT.
RT or MRT, or we can say NRT. Okay. So what exactly that exactly mean? That is PV PV by what that exactly mean? Then PV by T is equal to R, or is equal to your constant. Okay. This basically tells us that why only we choose this ratio, that is PV by T. This is because of that the at temperature that are comfortably in excess of critical temperature of a fluid, and also at very low pressure, the vapor of a fluid tends to obey this particular relation, that is PV by T. Okay, so if you going to talk about the critical temperature on the PV diagram, okay, and suppose if you have the water get converted into steam, okay, directly. So this temperature, okay, we generally call as, this is a temperature diagram, TV diagram. This temperature we generally call as critical temperature. So and very low pressure. So here we'll have a very low pressure at bottom. So at very high temperature and at very low pressure, okay, the vapor of the fluid at low pressure and at high temperature, the vapor of fluid obeys the equation or obeys the this particular ratio, and that is called as PV by T. So here in this case, the pressure at critical point, volume at critical point, and temperature at critical point is equal to pressure at very low point, that is called as PL, then volume at very low point, and the TL, temperature at very low point. So at very low vapor pressure and at very high critical temperature, we always get the relation called as P1 V1 by T1 is equal to P2 multiplied by V2 by T2. And this relation always used to be constant. Okay. So because of this reason, this only possible in the case of the perfect gas. So the gas or the fluid which obeys this relation at very high temperature and at very low vapor pressure, this particular fluid or gas we label as a perfect gas. So we can say that the gas which obeys this relation is called as a perfect gas, where this R is called as a gas constant. Okay. What is the unit of R? Unit of R is equal to Newton meter per kg Kelvin. Okay. Newton meter kg Kelvin. This we can also write down as, if this is kilonewton or joule, or kilojoule per kg Kelvin, or joule kg Kelvin. If it is in the kilonewton, then kilojoule kg Kelvin. Okay, so we are able to write down the relation called as PV is equal to your RT for m kg of perfect gas, and for V meter cube of volume, we can write down the relation PV is equal to mRT. Getting? Yes or no? All of you with me?
Yes, sir.
Yes, sir.
ये यूनिट कैसे है पता चला ना? ये PV न्यूटन मीटर केजी केल्विन.
Yes, sir.
Okay, pressure
Yes.
Newton per meter square. Okay, volume meter cube per kg. Okay, so meter square and meter will get cancelled, so there will be only one meter. So Newton meter per kg.
छोटा खींच ली घुस रही है फोटो खींचे ना तूने बहुत 14
Hello, any doubt? कौन
No,
बात
sir.
कर कौन बात कर रहा है? Any doubt? Please ask.
माय कौन था ना है ना
You.
PV by
Yagi,
T.
please unmute. Mute yourself.
Aggie.
त्यागी क्या चल रहा
I
है
am
बेटा?
muted. So I am
हाँ,
muted. I am
idiot.
muted, sir. Sir, by mistake.
So unit of pressure is Newton per meter square. Unit of volume meter cube per kg. Unit of temperature Kelvin. Newton meter kg Kelvin. Okay. If it is kilonewton, then kilonewton meter kg Kelvin. 1 Newton meter is equal to 1 joule. So it is a joule per kg Kelvin. If it is kilonewton, then kilojoule per kg Kelvin. यहाँ पर equal to मत लिखिए, and ऐसे कीजिए, confusion हो जाएगा. So we have equation called as PV is equal to your mRT. So on the molar basis, if you can talk about on the molar basis, this m we can define as n multiplied by m. Is it?
Yes, sir.
yes sir
And what exactly mean the molar basis? It's a quantity of gas which is equivalent to the mkg of the gas. Okay, so what we can say, the m is equal to n multiplied by capital M, where this capital M is called as, yes,
molarity
yes, molecular weight of the gas. What is n? N is the number of mole. So we can say that PV is equal to N M R T, or we can say MR is equal to PV by NT. So few times they asked in the examination prior to lockdown that prove that MR is equal to PV by NT. So if you concentrate, or if you recall the Avogadro's hypothesis, according to the,
excuse me sir
yes,
sir there is a difference in ideal gas and perfect gas.
perfect gas always obey this equation, ideal gas equation, but not ideal gas not always follow the perfect gas equation, because there is a difference between the critical temperature or critical temperature and what we can say the temperature associated with the low vapor pressure. So the perfect gas always follow this ideal gas equation, but the ideal gas, okay, not always follow the perfect gas equation, because there may be a variation of the PV by T, okay, in between the critical temperature and the very low pressure, very low vapor pressure. But by and large, with a macroscopic approach, MACRO, we always say that PV is equal to MRT in all the perfect gases of the ideal gas equation or perfect gas equation. Getting? Hello?
Okay, sir. Thank you.
Avogadro's. According to the Avogadro's hypothesis, what the hypothesis is that the volume of 1 mole of any gas, okay, the volume of 1 mole of any gas is the same as the volume of 1 mole of any other gas. When the gases are at the same temperature and the pressure. So whether it's the hydrogen, whether it's nitrogen, whether it's helium, whatever, volume of 1 mole of any gas, okay, is same as volume of 1 mole of any other gases when the gases are at the same temperature and at the same pressure. So we can say that according to the Avogadro's principle, the volume, that is V by N, this ratio is same for all gases at the same value of pressure and temperature, yes or no?
Yes, sir.
So V by N, this ratio is same for all gases at same temperature and same pressure. Okay, so we can say that the PV by NT, this PV by NT, that is V by N, okay, at same pressure and same temperature for all the gases, the V by N is constant, is same. So we can say that the quantity PV by NT is same and is constant for all gases. Yes or no?
Yes,
Hello?
sir.
So PV by NT is same. Okay. Or constant for all gases. And this constant we generally call as universal gas constant. That is PV by NT. Okay. E is equal to your universal gas constant, that is nothing but called as R0, where R0 is equal to your universal gas constant. So PV by NT, we know that, we just now proved that MR is equal to PV by NT and PV by NT is equal to R0. So MR is equal to your R0 is equal to your PV by NT. So we can say that PV is equal to N R0 T. It's a T, huh? R0 T. Since we know that this MR is equal to R0, since MR is equal to your R0, then the value of R is equal to R0 by M. Okay. And what is R0? R0 is equal to PV by N multiplied by T. So if you want to find out the value of R0, then for the R0, the volume of, yes, the volume of 1 mole of any perfect gas, okay, at 1 bar, okay, at 1 bar and at 0 degrees Celsius is approximately is equal to 22.71 meter cube, and we'll take the help of this data. So R0 is equal to 1 bar, that is R0 is equal to PV by NT. PV by NT. What is P? 1 bar, 1 into 10 raised to power 5, that is Newton per meter square, convert into that. And what is the value, or what is the volume? Volume occupancy is 22.71. 22.71. It is standard one. So it is the volume of approximate volume occupancy of 1 mole of any perfect gas at 1 bar and at 0 degrees Celsius. What is N? That is 1. What is T? Is 273.15 Kelvin. 0 degree plus 273.15 Kelvin. So it is a 273.15 Kelvin only. So if you solve this, then we are able to get the value of R naught, and R naught comes around 8314.3 Newton meter, PV is Newton meter per mole and Kelvin.
Kelvin.
So many times they ask this derivation that prove that value of R naught is equal to 8314.3 Newton meter per mole Kelvin. So if the value of R naught is given to you, and if you know the type of the perfect gas or the ideal gas, then you can easily find out the value of R. Yes or no?
Yes, sir.
Yes, sir.
So this relation is very important with respect to the numericals. Okay. So in the today's lecture, we see in the few basic fundamental concept that is called as process, cycle, quasi-static process, then isobaric process, isochoric process, isentropic process, isothermal process, adiabatic process, polytropic process. Then we move in the different form of energies, that is work and heat. We try to understand what exactly mean the work, then how the heat flow takes place. Then we talked about the reversibility and irreversibility, the causes of irreversibilities. We also discussed about the various examples of the irreversibilities. Then we move into the perfect gas. We try to understand what exactly is the perfect gas. A perfect gas is the gas which obeys the relation PV by T at critical temperature or above the critical temperature, and at also a very low vapor pressure. Okay, so that type of gas we generally call as perfect gas. And for the perfect gas, with the help of the Avogadro's hypothesis, we try to establish the relationship between the gas constant and universal gas constant and molecular weight. And we come to know that R naught is equal to 8314.3 Newton per mole Kelvin. It is the value of R naught. Getting home, all of you with me? Getting? Yes or no, please?
Yes, sir.
Sir, can you slide little bit up?
Yes.
Sir, more. Okay, sir. Okay. Thank you, sir.
कोई डाउट है तो पूछिए, अगर डाउट है तो पूछिए.
No, sir.
Okay. CR, you can please float the attendance to me. So can I conclude the session?
Yes, sir, all present.
All present. So you float the attendance to me, okay, on my personal WhatsApp number, not in the group. CR, please take care of this. So
Yes,
that
yes, sir.
so that I will maintain the record, okay?
Yes, yes, okay, sir.
Yeah. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you very much.
Jain, sir.
Jai Hind, Jai Hind.
Vande Mataram.
Recording in progress.
So right now we have got 17 students are there. Class strength is 35, no?
34. 34. ma'am.
34.
34, huh? So half the class only is here. So just tell everybody to join quickly, okay? Nimesh is the CR, isn't it?
Yes, ma'am.
Nimesh. So where
Yes,
are
ma'am.
all your friends? Tell them to join quickly.
Yes, ma'am. Yes, ma'am.
Hmm. In another 2 minutes, I'll start, okay, Animesh?
Yes,
So in
ma'am.
the-
Yes, ma'am. I had a message on our group.
Yeah, just message on your group and tell everybody to join quickly, okay?
Yes, ma'am. I had message.
So while they are joining, what we can do, just whatever was done in the previous class, that we can just revise it, okay? While the other students are joining, then after that we will continue. So my screen, is it visible to you?
Yes, ma'am.
Students?
Yes, ma'am.
It's visible, no? Yeah, very good. All right, so we have started with our topic on differential equations, right? Now what you have to do, you have to look into your notebook. Hopefully everybody has made the notebook and everything. Yes or no? Students of
Yes,
division 2, you have made the notebook, no? Yeah, very
Yes.
good.
Yes, ma'am.
So you will look into your notebook and you will start confirming one by one, okay? First we have seen definition of differential equation. Is that correct?
Yes, ma'am.
Yes, ma'am.
Then we saw some examples also. Here many examples we had seen of the differential equations. Then we saw the types. In this we saw ordinary differential equation and partial differential equation and then the supporting examples. Is that correct?
Yes, ma'am.
Yes, right. Then these are some common PDEs. Out of that, 2 of them we are going to see when we do the applications. Okay, then we saw this concept of order and degree. Is that correct?
Yes, ma'am.
Yes, ma'am.
Yeah, so for that also we saw the examples. Then while finding order and degree, I told you that you have to get rid of the integral sign or any other radicals, etc. And then only you will report the order and the degree. So all these things also have been completed. Then after that, we just saw the definition of solution, right? Then after that, what we did, formation of the differential equation. Is that correct? Yes or no? You can look
Yes,
into your
ma'am.
notebook and just confirm. Yeah.
Yes, ma'am.
So for this formation of the differential equation also, we saw some examples, right? And
Right.
then after that, what we did, we started with the solution of the differential equations, right? In that,
Yes.
the first method is variable separable, correct? So in variable separable, what we are doing, we are ensuring that variables of one type are,
Separated.
isn't it? So something like this, you can write. So this will
In
become
the
a variable separable part.
in
If
the
it is not variable separable,
class join कर ले. अरे
हाँ,
Shagi.
Harsh Yadav, you have to mute yourself. Harsh Yadav. Okay, now when we are reducing to variable separable, supposing it is not variable separable, how do we reduce it? By using a suitable substitution, isn't it? See, either you can use which one, y equals to vx, or you all can answer all this we have done, or what else? Yeah, students of division 2, be sharp. X is equal to Vy, or any other suitable substitution as per the requirement in that particular problem. All right, then after that, we had seen this Leibniz linear form. Is that correct? Confirm it. Yes, we
Yes,
had
ma'am,
seen,
correct.
isn't it? So this is the definition. This is our Leibniz linear equation. Then we saw the method of solving this equation also, where we are finding out the integrating factor. Then after finding out the integrating factor, then we are using this formula and finding out the solution. So I think we had finished up to this point. Then we saw one supporting example also for this Leibniz linear equation. Then after that, we were seeing this Bernoulli's differential equation. Is that correct? Have we got up to this stage?
Yes, ma'am.
We have got up to this stage, right? So you have noted this theory part or not noted the theory part?
Noted, ma'am.
You have
Yes,
noted
ma'am.
it. Okay, very good. All right. In the meantime, just one, before we do this Bernoulli's, just one short video clip I'm going to show you. You just observe it and then you tell me what you have observed in that video clip. Okay. Just give me a minute. I will just stop this share. And after that, I will. 1 minute. Just give me 2 minutes, students. I'll just open the. Okay, are you seeing this clip which has come on the
No,
screen?
ma'am.
Huh? No? Okay,
Yes,
just
ma'am. Yes.
you are seeing. Okay.
Yes,
All
ma'am.
right. So it's a very short clip, but you have to make some observation. And once it finishes playing, then you are going to tell me that observation. Okay. Yeah. Did you see? It's only 43 seconds. Do you want me to replay again?
Yes, ma'am.
Ma'am.
Yes, ma'am. Yes, ma'am.
Or this time you have to be very observant. Okay. Again, I will replay. Got it? What did you observe? Tell
Yes,
me.
ma'am.
Who will tell me? If you observed very keenly, something you might have noticed over there. Let's see.
First of all, he took the derivative of y to get more clear and more
Okay.
accurate. He started to integrate it,
Okay.
and
Then he used solution of differential equation, variable separable.
Okay, variable separable, solution of differential equation, fine. What else?
in short, he tried to get the more accurate answers by using different steps.
By using different steps. Okay.
Different methods of mathematics such as derivative, integration.
Nahi, Papa. We are solving only differential equation, isn't it? Yes or no?
Yes, ma'am.
So what is your observation? There is one small thing over here in this clip which you had to observe and tell me. Okay, I will replay it once again for the third time. For the third time now, be very careful. Because it's only 43 seconds. So be sharp and observe again. Now, who will tell? Yes.
He kicked something like what is theta plus.
No. See.
Is he
now,
trying to make y independent so he can get it?
No. He is just trying to solve the differential equation, isn't it? Yes or no? See this?
Yes, ma'am.
Right. So what is the integral of cos? Tell me, students. Integration of cos t dt. Basic
Sin t.
sin t. So what had come on the screen? What had come on the screen?
Okay, minus sin t.
So that is what you were supposed to have observed. Okay, so now I will just stop this here. All right, and we'll go back to our yes, what we were doing, Bernoulli's equation, right? Is the PPT visible once again to you?
Yes, ma'am.
Yes, ma'am.
So the point behind showing you that small clip is in differential equations. I've kept saying it in the previous classes. So one more time I will repeat, which is the most important skill that you should have to solve the differential equation. What you should be able to do perfectly.
Integration.
Integrate. See, because what I told you, solution means only integral. One more word for the solution is integral. So therefore, you should be able to integrate. So that those are the things that you should be able to catch. Okay. Now we are going to talk about this Bernoulli's differential equation, right? Now, of course, there are interesting stories about the things, discoveries and all that. There is one more equation also, which I don't know if you have heard of. It is simply called as Bernoulli's equation. Has anybody heard of that one? No?
Maths.
Probably you may or may not have heard. In physics, have you heard of it?
Yes, ma'am.
You have heard of it. Okay. So it's like, so the person Bernoulli who discovered this equation is different from that Bernoulli, okay? The surname is the same, but the people are different. So that Bernoulli's equation which you do, that is mostly used in hydrodynamics, okay? So that is a different one. So don't confuse the two things. So that was Daniel Bernoulli who discovered that equation. And this is Jacob Bernoulli who has discovered this one. Okay, now let's get back to our topic. So we have seen Leibniz linear equation. I will write one more time over here, dy by dx plus py equals to q. This is our Leibniz linear equation. Now you have to tell me by observing this one, what is the difference between these two? What will you immediately come to know? What is the
Y
difference?
to the power n.
Y raised to power n.
Y raised to power n, it is additional term over here. Now, because it is y raised to power n over here, this stops being a linear differential equation. See, if you have this kind of a term where this function, remember how we got the differential equation? By differentiating a function, right? So what I told you in the definition of differential equation, it is the equation which consists of the function and its derivatives, right? General definition. So over here, if this function is present with the power which is higher than 1. So here you can see n belongs to the set of real numbers, but excluding 0, also it should not be equal to 1. That is one more additional thing which I'm telling you. Okay, otherwise it will still be a linear equation if this n becomes equal to 1. So we don't want that. We want to reduce this to a linear form and then we want to solve it. So you just keep it in mind that to start with, this Bernoulli's differential equation is a non-linear one. But as of now, you don't know any method of solving non-linear differential equations. You know only about the first order, first degree differential equation, the methods which we have seen so far. So we will be highly interested in converting this to this form. We want to convert this Bernoulli's differential equation to Leibniz linear form. Then we are going to solve. This much, is it clear to you? This first thing what I've told you. Clear or not, students? This first part, what I just told you, is it clear?
Yes, ma'am.
This is non-linear. Why it is non-linear? Because we have got this term over here, y raised to n, right? So we want to convert it to this linear form and then we are going to solve it just as we solved our Leibniz linear equation. Okay, so now the important thing is how to convert to this linear form. So for that, there is some method for doing that, right? So let me just show you. First thing, you all in your notebook, you write this heading. Write this heading, write this part, this equation. Then I'm going to bring up a new screen and over there, I'm going to show you how to convert. So I'll give you 1 minute. You just write down so much. Heading and this equation, this much you write. Yeah, once you have finished writing heading and equation, just tell me so that I will be able to continue then.
Done, ma'am.
Done.
Done,
Okay,
ma'am.
very good. All right, very good. So now, just I will bring up a new screen. Okay, so see here. So dy by dx plus py is equal to q y raised to n. So already I've told you the conditions for n. Now our aim is that this equation, we want to convert it to this form, dy by dx plus py equals to q, so that we will find the integrating factor and all that and solve. So this is the objective. So for that, what we are going to do, the first step, we will divide both the sides by this y raised to n. So what I can write, y raised to minus n dy by dx plus over here, this will become p y raised to 1 minus n is equal to q. This much is clear to everybody, this first step.
Yes.
What we did, we divided by y raised to n, because see, in this equation over here in our linear form, we don't have any y raised to n in the RHS. So I want to get rid of that. But at the same time, you can see that this derivative also does not have any coefficient. So I just want simple dy by dx. So I don't want this additional term also. So for getting rid of this term, what I do, I make one substitution. What is going to be my substitution? Let y raised to 1 minus n, let it be equal to v. So what I've done, I've changed the dependent variable from y to v. Remember, if we write our equation like this, y is equal to fx, Which is the dependent variable and which is the independent variable? Tell me.
Y is dependent and X is independent.
Yes. So over here, what I did, I changed the dependent variable from Y to V. Okay, because I want to get rid of this coefficient over here. Now, obviously, I must also write the corresponding derivative. That means dy by dx will change to dv by dx. But for that, we have to differentiate. So 1 minus n. Now, simple principles of derivative we are using. Okay, first principles of derivative, everybody should be knowing this. And this will be equal to dv by dx. Okay, so therefore, what I can write? Y raised to minus n dy by dx is equal to 1 upon 1 minus n dv by dx. This much is clear to everybody? This part, how we did the substitution, then we
Yes,
differentiated,
ma'am.
Yes,
and now
ma'am.
we have got this, right?
Here.
So what I can do is I can just give these equations. If I want for convenience, I can give some number. So I can call this as equation 1. I can call this as equation 2, just for convenience. I can call this as equation 3. So whatever I have obtained the expression in equation 3, I will substitute it in equation 2. And now what I will get? 1 upon 1 minus n dv by dx. Okay, plus PV is equal to Q. And now one last step, what I will do, I'll just write this as dv by dx. I'm going to cross multiply this 1 minus n to P. So P into 1 minus n into V is equal to Q into 1 minus n. Now, what do you think? Have we arrived? Have we got this form? Just compare and tell me. Have we got the form? Remember, n is a constant. Okay, so it is going to get merged with this P. Similarly, here also n is a constant. So I have given you the conditions for n. So this is going to get merged with Q.
Yes, ma'am. It is matching. We get answer.
It is matching, isn't it? Now, after that, the rest is exactly the same way what we did for the linear equation. So for that, what we are going to do, we are going to find the integrating factor. Now over here, we will find integration, e raised to integration. This whole thing we are going to integrate. And then as usual, we are going to write the solution, v into integrating factor and all that, and then reconvert this v to y. So that part already you are familiar with. So this is just the theoretical approach I have told you. Now we are going to solve the actual example, which is based upon this approach. So any doubts, anything up to this step? Are all the things clear to you?
Yes,
Any-
ma'am.
Things are clear? Okay, very good. All right, so we'll just go back over here. Yes. So this is the same thing. Have you noted or not, students? Did you note
Yes, ma'am.
everything?
Noted.
You have
Noted, ma'am.
noted. Okay, very good. All right. So fine, now it is time to apply this. So this is our problem statement. Okay, this is our problem statement. So is this the Bernoulli's differential equation? Yes or no? Is it?
Yes.
Yes. Why it is so? Because you are seeing this additional y raised to 6. It is non-linear. Now we have to follow the same steps. So let's see, at least first step, you all can easily tell me, what should I do?
Divide by y6.
X should be
Divide by y raised to 6. Yes, okay. First step, I will just divide. So what I will write? Y raised to minus 6. Your x is also there. Dy by dx. Plus y upon y raised to 6 means y raised to minus 5 is equal to, now this will be x cube. But now I don't want this additional x also. So I will also divide by x. So dy by dx plus y raised to minus 5 divided by x is equal to x square. Okay, now who will tell me the substitution? Very easy. What I should substitute now?
Y raised to minus
minus 5.
Y raised to minus.
Very good. Yes, let y raised to minus 5 be equal to v. Correct. And now we will differentiate. Again, this is a very simple derivative. So minus 5 y raised to minus 6 dy by dx is equal to dv by dx. And now what we will do, we will just write y raised to minus 6 dy by dx is equal to minus 1 by 5 dv by dx. And next step is, of course, we are going to substitute, and this equation, what it will become, minus 1 by 5 dv by dx. Okay. And this is plus v upon x is equal to x square. Up to this part, everything is clear. Whatever we did
Yes,
in the
ma'am.
theory, that same thing we are doing. Okay. So just remember like when we discussed the CHLP in the first class, remember I had described to you that the prerequisites for this particular topic, this chapter, is that you should know the basic trigonometric identities, and then you should know basic integration and differentiation, right? That means all the relevant formulas and everything. If that much you just familiarize yourself with, then everything is fine. Okay, now we are going to fine tune all this. So we will write this as dv by dx minus 5v divided by x is equal to minus 5x square. Now, is it in a linear form? Just see. Is it in the linear form? dy by dx plus py is equal to q. Do you see that it is in that form? Division 2 students. Have we obtained the linear form? Sorry, what happened?
Yes, ma'am.
Are there? Okay. So in this particular case, just tell me what is P and what is Q? What is P?
Is minus 5.
Minus 5 by x. Okay, very good. And what is Q?
Minus 5x.
Minus 5x square. Okay, very good. All right. Now we have to find the integrating factor. So integrating factor e raised to integration p dx means integration of minus 5 by x dx. Once again, this is a very, very simple integral. So who is going to tell me this? Integration of minus 5 by x. Very simple integral.
Minus 5 log x.
Minus 5 log x, isn't it? But now we will use some things, basic identities of logarithms. So minus 5 log x means we can write it as log x raised to minus 5, right? Yes or no?
Yes,
Yes,
ma'am.
ma'am.
Minus 5.
So e raised to log x raised to minus 5 means how we can write this finally?
X raised to power minus 5.
X raised to minus 5. Fine. So this is our integrating factor. Now we are going to find the solution. So dependent variable over here is v. So v into integrating factor is equal to integration. Now q. So q is minus 5x square into integrating factor x raised to minus 5 dx plus c. Now once again, this is a very, very simple integration. So minus 5x square into x raised to minus 5 dx. So you only tell me. I'll expect the answer from your side. Very simple integration. So x square into x raised to minus 5 means it will become x raised to minus 3.
Minus 3.
X raised to minus 4.
Minus 4.
X
5 by
minus 3.
Minus, yeah.
Ma'am, final answer 5 by 2.
5 by 2 x
X
raised
raised to
to
power minus 2.
X to
minus 2, isn't it? See, when you first time,
Yes.
whenever you studied integration, that time the first formula which you learned
N
was
plus
this
1.
one, isn't it? X raised to n plus 1 divided by n plus 1. Yes. So that one we are using over here. Plus c. Now see, we had put y raised to minus 5 as v, isn't it? So we have to resubstitute. So we are going to write y raised to minus 5 into x raised to minus 5 is equal to this 5 by 2 x raised to minus 2 plus c. And that is the solution which we have obtained. Idea is clear to you or?
Yes, ma'am.
Yes, ma'am.
Now I had also, I kept telling you in the previous class, once again I will repeat, if you want to express the solution in the traditional way of y is equal to fx, yes, by all means, you can simplify the expression by transferring this x raised to -5 to the right hand side. All that can be done. But while you are simplifying, make sure that you are simplifying and not making the expression more complex. Otherwise, you just leave it here as it is. We have obtained the integral value, and that is the solution of the differential equation. Is this clear to you? Bernoulli's differential equation. Is it clear or not, students?
Yes, ma'am.
Sure, everybody?
Why you write constant before integration?
Why we write constant before
Ma'am,
integration means?
like in the final answer, before the final answer is integration minus 5x squared dot x minus 5 dx plus c.
That we have just used the same formula. We are following the notation. See here. This, even if you don't write at this step, it is okay. All right.
Yes, ma'am. Okay, ma'am.
So don't worry, it will not be marked as incorrect or anything. Whenever we have an indefinite integral, that time we must present the constant of integration. That simple thing, just to keep it in mind. Okay. All right. So this Bernoulli's differential equation, is it clear to everybody? Yes or no? Some response, students. Division 2. It is clear. Okay, very
Yes,
good.
ma'am.
All right. Before we continue with the next type, now just let me just share one small thing with you. Okay. So, can you see my new screen? Can you see this new screen? You can see?
Yes, ma'am.
Students. Yeah. So here, this is like, the differential equation in action. Let us call it like that. See, this is our differential equation. Dy by dx is equal to x plus y. Which type is it? Can you identify the type?
Circle.
No. I'm just asking you the type of differential equation. See, just now we saw so many, no? So how we are going to go about solving this? In other words, let me rephrase my own question. Which method you will use to solve this differential equation? See, dy by dx is equal to x plus y. Which will be this type? Very easy question, students.
Leibniz.
Leibniz, sure? Are you sure? Whenever I ask like this, you should be 100% sure.
Yes, ma'am.
100% sure. Okay, very good. So we can rewrite this like this, no? Dy by dx minus x is equal to minus y is equal to x. Is that correct? Yes or no?
Yes, ma'am.
Then in that case, this is similar to your dy by dx plus py is equal to q. Okay, now students, one small exercise I'll give you. Solve this differential equation and tell me the solution quickly. This is a very easy one. You will be able to find integrating factor and everything. Do all those steps and just report the final answer to me. Yeah, by now you would have finished finding integrating factor and all that. Whoever
yes, ma'am.
finishes, yes, okay. Have you finished the solution?
Yes, ma'am.
Okay,
Yes,
very
ma'am.
good. Just tell me your answer, whatever you got.
Ma'am, the integrating factor which I got is e to the power minus x square.
That is okay. Now you just tell me your final answer, what you got for solution.
Yes,
Just the
ma'am.
solution.
Y
okay.
into e
Uh-huh.
to the power minus x square is equal to minus 1 by 2 e to the power minus x square plus c.
Okay, 1 second. Y into e raised to minus x square is equal to
Minus 1 by 2
uh-huh.
e to the power minus x square plus c.
Plus c. Okay. All right. Anyone else? Anyone else? I will just write your answers here, whatever you are telling me. See, your are you sure you have done everything properly? Who told me this answer?
How it is x square?
Huh?
Will it be y
Five by
square?
two
Or
होगा.
x.
Ma'am, yx होगा.
Okay. Somebody else wants to try. You also tell me. I will write all your answers. Then we will check it. Whatever you're telling me. Now, this is the first answer which is comma.
Y plus x equal to minus 1 plus c.
Okay, 1 second. Y plus x is equal to
Minus 1 plus c.
minus 1 plus c. Okay, see, now these both the answers are totally different. Anyone else? Third answer. See, over here, I don't know who gave me this answer. You just check yours, huh?
Yes, ma'am. Yes,
This one, there is some major mistake you have made.
yes ma'am. I understand.
You got your mistake.
Yes, ma'am. Just
Okay, so this I will cut it. Now, next one. Is this okay? This answer, is it okay? Just check again once, students.
Integrated factor will be e to the power minus x.
Tell the final answer. Only final answer I want. You have something different than this one? Quickly. This is also not okay, whoever told this. This one is also not okay. Yeah, third try, third attempt. See, the solution is there on that diagrammatic solution is there. That diagram which corresponds to the solution with that green colored line which you're seeing, that curve, that is there. So obviously it is not linear. It is a non-linear equation. So this one also I am going to cut it. Now who will tell me this third attempt should be correct one? Who is scoring high marks in the maths one? Who has scored very high marks? That student can tell me. Students, this type of a sum in the exam, you'll get hardly maximum 6 to 7 minutes to solve. So now you have to really hurry up. What is the integrating factor?
Y into e to the power x, ma'am.
Okay, you're telling the answer. Are you telling the answer to me?
I will try, ma'am.
Go try so far. You have to finish solving, no? All of you have to do this. This answer I expect from your side. Okay.
Answer is
Answer is
y into e to the power minus x
okay. Y into e raised to minus x. Okay.
equal to
Hmm.
e to the power minus x common.
Okay. E raised to minus x common, no?
Yes, ma'am.
Okay.
Bracket
Hmm.
minus x minus 1
Minus x minus 1. Like this way?
plus c. Yes, ma'am.
Plus c. Okay. All right. Okay, fine. Yes. So your integrating factor is obviously over here e raised to minus x. So this part is correct. Then you will be doing integration of q into integrating factor. So x into e raised to minus x dx plus c. So your answer is correct. Fine. Very good. Okay. Now you look at the screen, students. Look at the screen over here. Okay. And I'm going to make some changes in this diagram. Okay. Because already we can make it over here. And you tell me what is happening. See, solution A is tick marked over here. Now I'm going to tick mark this solution B. You are going to tell me what change is taking place. All right. Just let me see what is happening. Observe and tell me according to you what is happening. It is the same differential equation. But when I tick marked solution A, once again you see, I'll just remove this. See, solution A, some curve is there on the screen. Now solution B, again you can see the nature of the curve, how it is. Solution C, see the nature of the curve. Solution D, see the nature of the curve. According to you, what do you think is happening? Let's see who will just quickly be able to identify what has happened over here. The solution is the same only, isn't it, of the differential equation? That one is not changing, but something has changed because of which the nature of this curve has changed every time that I clicked on these particular boxes for solution A, B, C, D. So according to you, what changed? Anybody will be able to tell me? What do you think changed? Anyone? See, don't be afraid to answer. At the most, your answer will be wrong, isn't it? What is there in that? There's no issue. Just to think and you tell me, you do the observation. See, once again, I will just remove this. So this is one solution. Now I will just tick mark another one. See, solution C. How the nature of the position of that curve has also changed. So what is changing actually? Can you identify what changed? Or you can take a screenshot and you can tell me in the next class also if you want. That is not an issue. Right away, if you're not able to tell, that is also fine. Just take the screenshot. Then next class you think and you can give me the answer that time also. Is that okay? Will you do this for a homework?
Yes, ma'am.
Division 2 students. So this is your homework. You take a screenshot of all this, what is there on the screen, what you're seeing. And then you give it a thought. You can discuss amongst yourselves also if you wish by the WhatsApp or whatever. And then you tell me what do you think changed such that the nature of this curve changed. Is that okay? All right. Okay, fine. Very good. So now we'll just continue with what we were doing. Yes. So we had completed this Bernoulli's differential equation. Is that correct? Yeah. Now we are going to do the last one. So today's class, let us see if we have time to solve the exact differential equation, we will solve it. Otherwise, I will just tell you the definition and all the other things, supporting things, and then we will stop over here. All right, so now we are talking about one more special type of differential equation, which is called exact differential equation. Okay. So for that, see, first of all, we start with the differential equation and just notice how this is a m dx plus n dy equals to 0. Okay, now there is some theory behind this, how this 0 and all actually. So actually, you know, this the reason why we call it as exact is this is actually a total differential or a full differential. That means this right hand side part, we can express it as some du. Okay, where u is some function of x and y, and especially this du, it is equal to 0. This is the special part. If it is not equal to 0, then this function, this particular differential equation, it will not be exact. Okay. So you just note this. If m dx plus n dy, where m is a function of x and y, n is a function of x and y, also it can be only function of x or only function of y, or it can be combined with a constant also. So all those variations are possible for m and n. So for this type of a differential equation to be exact, this condition has to be satisfied. Everybody knows about the partial derivatives. All of you know partial differentiation.
Yes, ma'am.
You know partial differentiation. So you can see here dou m by dou y means partial derivative of m with respect to y should be equal to partial derivative of n with respect to x. This is called as condition for exactness. See, now such things, students, please don't ignore this, that this is some theory and all. Of course, we are going to use it while solving the problems. But even from the exam point of view, let me tell you, if the paper pattern remains the same as like it was in the previous semester, then you have some objective questions also over there in the paper, isn't it? Yes or no? Yes or no? Division 2 students.
Yes, ma'am.
Yes, ma'am.
So in your objective question, this can be with the type of question. Condition for exactness is, so what? Dou m by dou y is equal to dou n by dou x, like this way. Okay, now, so once this condition is satisfied, how to solve? So solution is given by this formula. Integration m dx, where we are going to treat y as a constant, plus terms in n which are independent of x. Okay. Now independent of x means do not contain x. Now this is also very typical type of differential equation. Okay. Once again, it has many applications because of this very property that it is a full total differential. Okay. Because of that itself, there are typical type of applications which make use of this exactness property. All right. So integration of m dx, where y is a constant, and integration of terms in n which are independent of x. And this integration will be with respect to y is equal to c. So this is the theory part of it. Does anybody want to ask me any question, any doubt, anything? Students of division 2. Doubts, if you want to ask in the class, you can ask in the class. Later on also, if you want, you can contact me, as I've already told you in the earlier previous classes also, by the WhatsApp, email, phone, whatever. Okay, as per some suitable time. Okay, if it is clear, then just note down. You need not note down each and everything which is there on the slide. You can just write the equation. You can write the condition of exactness. And then you can just write this formula or the solution of the exact differential equation. And how much time is left? After this, do you have a class? Do you have a class?
We have snacks.
Yes,
It is
ma'am.
your snack
Ma'am.
time. Okay,
Yes,
snack
ma'am.
time is there. Okay, okay. So then I will not delay you. You take down this much. Then next class, we will solve the example. Okay.
And please repeat solution.
See, solution. First, you understood what is m and what is n. This you have understood, no? M and n, what are they? They are either functions of x, y, or they can be functions only of x or only of y, or maybe along with some constant also. Okay. So generally we are writing mx, y and nx, y. Okay. So integration of m dx, where while integrating, you are going to treat y as a constant. That is why I have written like this, y constant. plus integration of those terms in n which are independent of x. Okay. See, supposing I say like this, let me write down only. Supposing I say n is equal to x cube plus x square y plus y cube. Tell me which term is independent of x or which does not contain x. Just tell. This is n.
Y cube.
cube.
Y cube. Okay, so that is the meaning of this statement. Terms in n which are independent of x. And of course, that means it will contain only y, or maybe it will be even a constant. Okay, that is also possible. If I just change this, suppose I make it xy cube plus 6. In that case, which term is independent of x? Tell me. 6. So it can be term containing only y, or it can be some constant value also. Okay, or it can simply not be there. That means, let me again put one x over here. Now, is there any term which is independent
No,
of
ma'am.
it? No. In that case, you will write 0 or leave it. Just put c over there. That's it. So terms in n which are independent of x. So you will integrate with respect to y is equal to c. So this is the part. So yes, it is hardly just couple of minutes. I think going by the strength today, everyone is present. CR, confirm.
Yes, ma'am.
So no absentees.
Yes,
Okay,
ma'am.
very good. So your class is maintaining a good attendance recorder. Right from the first lecture, I am seeing that there are nil absent. Always number of students who are absent is nil. So you please keep it up. Okay. Yeah. All right.
Okay.
All right.
Thank you.
Students, now that's it from my side. Okay, for today's class. We
Good.
will stop over here.
Thank you, ma'am.
Thank you. Thank you, everybody.
Jai Hind, ma'am.
Jai
Jai Hind.
Hind. Have a nice day. And thank you. Okay. So I'll
Thank you.
end the session.